Hello, this is Jonathan Doolin, and I am recording a response to a paper called Planetary Core and Surface Temperatures by Douglas J. Cotton, and it was published in the, what was it, SSRC, there it is, SSRN Electronic Journal, January 2013. I've already covered sections 1, 2, 3, 4. When I got to section 4, I decided to skip forward to section 6, or was it? And when I got to 3, I skipped forward to section 6, and eventually I assented to the propositions made in section 6. Then I went back to section 4, and now I am ready for section 5. What I've discovered, though, in section 5 is essentially an argument supporting a proposition to which I have already assented. So here is what it looked like on the piece of paper, where I went through Wikipedia's equations versus my equations, figured out, okay, yes, they match. This one I wasn't quite sure because there was a negative sign and I had a positive sign, but this just depends on whether this actually just depends on whether you define W to mean work on the gas or work done by the gas. So that's probably where the difference in sign came from. And finally, down at the bottom, I ended up agreeing. I noticed that it says assuming no loss due to friction, and since this is an adiabatic process, there will be no loss due to friction. And I had to come to the conclusion that yes, the dt dz would be equal to the gravitational field divided by the specific heat at constant pressure of the gas. However, I did not agree with the conclusions that came out of that necessarily, because my proposition would be that if we only had O2 and N2 in the atmosphere, then the result of that gradient would be that at the surface of the Earth we would have a temperature of 255 Kelvin, and out here at the top of the troposphere, or the tropopause, we would have approximately 155 Kelvin temperature. But because we have greenhouse gases, we have the temperature at the tropopause of 255 Kelvin and at the surface of 288 Kelvin. But we're not getting to that part in section 5. We have to wait till section 7 to actually get to the part where he's actually making that argument. For now, though, he's talking about the things that I've basically assented to. And his argument in this section, I think I'll just summarize it a little bit rather than go through every detail, is basically that the potential energy, let me see if I can find the sentence. It is clear the state of greatest entropy is the state in which the mean sum of molecular potential energy plus kinetic energy is the same within all regions of the cylinder. So make a graph of that. If we have the height right here, the potential energy goes up as we increase in height, and so the kinetic energy would have to go down as we increase in height. And if you take the sum of potential energy plus kinetic energy, this here, you get the same value as you get by taking kinetic energy plus potential energy here, or the kinetic energy plus potential energy there. So, and then the kinetic energy is essentially U, where PV equals nRT equals 2 divided by the degrees of freedom of the gas times U. So this kinetic energy is going to be related to the pressure and volume of the gas at that height and the temperature of the gas. So as a rule then, the temperature is going to be highest down here at the ground level, and lower up there at the tropopause or whatever. And if we had a temperature at ground level of 255 Kelvin and a temperature at the tropopause of 155 Kelvin, then that would be a great explanation of why that phenomenon was occurring. But that's not what we see. We see, at the tropopause, we see a 255 Kelvin temperature, and at the surface, we have 288 Kelvin. So this description is not an explanation for the actual data that we're seeing. So I'm actually going to kind of skip past this because it's everything in chapter 5. Basically, it's all a description of what I have already assented to. I have no argument with it. It's pretty well reasoned. I'm going to skip forward to section 7. I already did section 6. And in section 6 I came up with my own arguments for why this was the case. That temperature divided by height is equal to G over the specific heat. So going on to section 7, he says, there is a general perception that the so-called dry or wet adiabatic lapse rates occur in atmospheres as a result of the surface being heated by the sun and then convection flowing upwards. And that is essentially, okay, now we're arguing, because that's what I just said. Essentially, I didn't talk about the wet adiabatic lapse rate. I haven't looked at that very closely yet. If I need to, maybe I'll look at it, but right now I'm just looking at the dry. But my main premise was that the light comes in, it's absorbed by the ground is heated to an average of 255 Kelvin, and then that light is emitted from the ground, and basically higher energy particles from below strike lower energy particles up above, and as a general rule you can kind of think of that as the heat flowing from the bottom to the top, or you can just think of it as an equilibrium scenario where heat isn't really flowing any direction. But there is definitely a thermal gradient, that the top surface is cooler than the bottom surface. So what does he say about what I just said? He says this mechanism cannot possibly explain the observed temperatures because the sun could not heat the surface to the observed mean temperature. The observed mean temperature is 288 Kelvin, and he is right. He has failed to explain that 288 Kelvin. What he has done is explained 255 Kelvin. So he's not criticizing this model. He's criticizing his own model, unfortunately. So he's right. The dry adiabatic lapse rates do not explain the observed temperatures. Okay, because the greenhouse gas effect is not the same. Don't make no mistake, the adiabatic lapse rate is a different phenomenon than the greenhouse gas phenomenon. Okay, so as discussed, this is even more obvious on Venus, where the poles, for example, appear to receive less than 1 watt per meter squared of direct insolation from the sun, and the dark side receives nothing for 4 months, yet cools only 5 degrees Celsius. Okay, this is a red herring, essentially. If I've got let's say a 5800 Kelvin heat source over here and a 300 Kelvin heat sink over there, the way thermodynamics works is that this object will heat this object, and if no heat is lost, then eventually these two will come to an equilibrium. If this guy has a power source inside him, and he's continuing to send out energy, and let's say this is just one microwatt per second, not per second, 1 microjoule per second. So it's taken a very long time. So it's a very, very slow rate of heat exchange. But it lasts forever. What temperature does this end up with if that 1 microjoule per second just keeps going and never ends? Well, eventually, if this thing is powered and it stays 5800 Kelvin, so like by a nuclear furnace down in the bottom, uh, then this is eventually going to get up to 5800 Kelvin. Doesn't matter whether this is measured in watts per second or 100 watts per second or 1000 watts per second. If this is sending heat into it, the equilibrium temperature is 5800 Kelvin. Of course, it's not going to end up being that because this thing is going to radiate out in all directions. So it never gets up to 5800 Kelvin. But this idea that he's making here, that one watt per meter squared is just not enough intensity to do it. Well, that's not a valid argument, because it doesn't matter how slowly the equilibrium, it doesn't matter how quickly one gets to the equilibrium. It just matters where the equilibrium temperature actually is. So the max theoretical temperature that the sun could, the maximum theoretical temperature that the sun could impose on something is probably like 5800 Kelvin. All right. Okay, so he says, rather than convection being the only cause of the thermal gradient, it is apparent that the gradient is in fact established in still air at the molecular level by the conduction-like process we have been referring to as diffusion, involving molecular collisions which share the kinetic energy of the molecules involved. Diffusion, diffusion, diffusion. I think I may have skipped that. Note this is the first use of the word diffusion right here. Process is called conduction in a solid, although we will use the alternative word diffusion strictly in the context of sharing kinetic energy during collisions involving gas molecules. Okay, so what? Okay, that was in section 5. So down here in section 6, he mentions the diffusion again. We are in section 7. So diffusion, what he has just described, is the adiabatic lapse. Is like a word that he has used already for adiabatic lapse. And he has said adiabatic lapse can't be the mechanism to explain the observed temperature. And then he goes straight to saying the phenomenon of adiabatic lapse is the phenomenon. Well, hold on. I can't help thinking that he's gone completely off the rails at this point, because he's basically described this adiabatic lapse process as diffusion, and then he said that this adiabatic lapse process can't explain the observed temperatures, and then he said that diffusion actually is the process that causes the diffusion of kinetic energy, which will lead to the conditions in the horizontal plane. So he's going back and forth, arguing with his own proposition and saying that, and he's already said that the proposition that he has promoted can't be the answer, but he's also claiming that the proposition is the answer. All right. he's gotten confusing, but okay, now he's doing a thought experiment, and I feel better when we're just doing some thought experiments, because up to that point he's just doing putting words together, don't make any sense. So let us now imagine an experiment with a cylinder of gas. For the present consideration, we'll assume that no chemical reactions or phase changes take place, and that no other energy enters or leaves our well-insulated, sealed cylinder, which we will fill with pure nitrogen so as to rule out any significant amount of heat transfer by radiation inside the cylinder. What? Okay, the thing is, okay, pure nitrogen is transparent. So if the cylinder is dark, inside, that would rule out significant amount of transfer by radiation. But if the cylinder is warm, or or if it's warm, thus emitting infrared radiation, or it is got lights inside it, then there is going to be some radiation inside the cylinder. Of course, whether heat is transferred by that light is another question. All right. But it's kind of a non sequitur to fill it with nitrogen so as to rule out any significant amount of heat transfer by radiation, because nitrogen, pure nitrogen, is going to be transparent to virtually all radiation, and that won't rule out heat transfer by radiation. It just doesn't produce any. It's not likely to produce any radiation. Okay, but anyway, as you probably know, molecules move about in random directions, colliding at various angles with each other, with other such molecules. But as they move between collisions, they will be affected by the force of gravity, and just like an apple falling off a tree, when molecules move in a general downward direction, some of their potential energy will be converted to extra kinetic energy. The opposite happens when they move upwards, and so, as we saw in section 5, there will be a lower mean kinetic energy among molecules at the top than among those at the bottom. In other words, the temperature will be lower at the top and higher at the bottom. Okay, yep, we've already assented to that. You could also imagine a cylinder which has a removable insulated dividers that form 3 equal compartments. With the dividers in place, heat in the middle compartment. So he's imagining a situation like this. Then the low KE will go up here, high KE will go down here, and because of gravity, the higher kinetic energy will go down here, and the lower kinetic energy will go up here. It's kind of interesting, though, that there is a counter effect. That I just want to bring this up right now. There would be a counter effect that the higher kinetic energy gas would be less dense, and the lower kinetic energy gas would be more dense. So these high kinetic energy and low kinetic energy gases might actually end up sort of more likely to mix, because the density and their kinetic energy are both going to kind of fight against each other. So that's an interesting idea. Oh, but that brings us to the end of section 7, and we're on into section 8, the concept of heat creep. In this section, we will see that gravity, in effect, makes a sloping thermal plot into a level playing field in which energy can spread in all directions like a bucket full of water poured into the middle of a swimming pool. For example, let us consider what happens when a supply of extra thermal energy is added somewhere in the middle of this sloping thermal profile. The effect can be visualized by turning the graph of the temperature altitude relationship on an angle such that it is perpendicular to the gravitational force in the room where you are in. Turning the graph of the temperature-altitude relationship. Alright, so here was my graph. Height versus kinetic energy equals U. That is going to be degrees of freedom over 2 times nRT. So in essence, this is a temperature graph. The temperature is going down as we increase height. And what do they say to do with this graph? So temperature versus height. And turn the graph of the temperature-altitude relationship on an angle such that it is perpendicular to the gravitational force in the room you are in. That is, you make it look like a level playing field. So, what? We're supposed to do this so that the kinetic energy line is horizontal. Why? Or actually, it looks like he's got the temperature going vertical. So what would that look like? Well, we want like this. So the temp goes that way, and then we'd have energy over here going kind of slanted, joules, and height going in meters. Okay, that seems weird to me. Seems weird. Okay. My description, if I match this line here to this line here, I don't find that line is represented by potential energy plus kinetic energy equals constant. And also, if I compare this line here to this line here, I don't think that line has anything to do with energy at all. Although, I guess you could multiply it by the gravitational constant, turn it into something that has units of energy. Or at least GH is gravitational potential. I'm sorry, I just really want to just leave the graph alone. Have height be on one side, have energy be on the other side, and let's not turn it. But if we want to add some energy to the gas at this point, we can just say, yeah, let's add some kinetic energy to the gas. It's right there, and yeah, there's going to be if the heat transmits downward by conduction, then we would, if you add heat to the gas right here, we would end up with the kinetic energy plus the potential energy being at a higher sum. That's what would happen if we added that much energy to the graph. If we added that much energy to the gas, we would end up with both the kinetic energy and the potential energy being higher. So he goes on to say, now when a rainstorm falls on a section of the ocean, the extra water spreads out in all directions, eventually over the whole surface of the ocean, following the curved surface produced by gravity. So it is with the extra energy deposited in the atmosphere. If it makes the local temperature greater than the theoretical thermal profile would indicate it ought to be at that location. I'm not finding that much use in his analogy, but I think if what he means by that is that when you add energy to the gas, if you add kinetic energy to the gas at this level, then it increases the sum of the kinetic and potential energy all along the way. So by adding that much energy to the sum of kinetic energy and potential energy, you're adding that same amount to, let's see, yeah, once it obtains that hydrostatic equilibrium, it basically affects the whole graph. And you know what? I did this wrong. You know what's not going to change? That potential energy is not going to change. No. Potential energy is not going to change by adding heat to the system. Okay, let's fix that. Find my pencil. You can add kinetic energy to the system and then have it come to a new thermal equilibrium with a higher temperature. You can remove kinetic energy from the system and you'll have that same equilibrium with a lower temperature. So that is what's going on. So he says, but the extra energy actually creates a situation in which more molecules move outward than inward. Is that true? Okay, where was I? I left for a little bit, but it says the extra energy actually creates a situation in which more molecules move outward than inwards. And I'm seeing that raising the kinetic energy to a larger value will make those molecules be warmer. So they would be those molecules would have a higher linear kinetic energy, but I don't see why it would mean there were more of them moving upward in the environment towards greater height. And again, I don't quite understand his graph really well at all. But he says this was not the case with the pure diffusion process, where there were random movements. At least if the pressure gradient was not changed in the process. So this provides us with a distinction between convection, where there is an adiabatic movement of air, and diffusion of kinetic energy, which can happen in totally still air. In practice, both work together with the same result. Right now, I'm not claiming to understand his argument. I'm just kind of struggling along to see if there's anything I can grab hold of in any of this. It says, in general, convection requires an additional source of energy, and the most common form is that provided by the sun. When the surface absorbs solar energy, that energy then transfers from the surface into the atmosphere by conduction, diffusion, and then provides a continuous supply of extra energy, which creates convection. Okay. A consequence of the above discussion is the level playing field is that when a supply of latent heat is released from water vapor, there could be some downward convection apparently moving against the temperature gradient. The original energy shown in red in the above diagram now spreads out as shown in this diagram. The heat's going to transfer around, so overall throughout the atmosphere. On Earth, upward rising air by normal convection would probably overpower this to some extent, but the situation would be different on Venus because so little direct solar radiation gets through the thick atmosphere and into the surface. What must happen in order to explain how the Venus surface receives the required energy is to keep it so hot is that incident solar energy is absorbed at all levels of the atmosphere, and then it spreads out over the whole plane, just like rain falling on a section of a lake leads to extra water spreading out over the whole surface. Well, yeah, it does get absorbed throughout, probably. I mean, only 10% of the light reaches the ground. they said. Okay, the extra energy absorbed will only spread out evenly in all directions if there was already thermodynamic equilibrium in the region. What? You can only add energy to... Oh, no, it just will spread out evenly. Okay. But, I mean, who cares? If you're putting energy into the system, whether it's being added evenly or if it's added unevenly, it's just energy is getting there. When such equilibrium is established, the additional kinetic energy at some point unsettles the equilibrium. It is just as easy for the energy to spread up the thermal plane as it is to spread down the plane or in any other direction. So the thermal plane, even though it actually has a thermal gradient, acts like a level playing field because of the effect of the gravitational field. Hence we have this rather strange concept that additional energy can in fact cause heat creep up the thermal gradient to warmer regions, providing that there was thermodynamic equilibrium initially. This process explains how energy can get to the base of the atmosphere and keep it warm or very hot on Venus, quite independently of any energy received back at the surface. Okay, so once again, here's a plot. The kinetic energy of the gas, which is proportional to the temperature, versus the potential energy of the gas. And we're going to suddenly say that light comes in through the system and it hits a patch of atmosphere here at this height. Then the kinetic energy of the gas rises there. And then that energy is going to distribute throughout the atmosphere and increase the kinetic energy like this. So basically that additional kinetic energy is going to distribute itself throughout the atmosphere so that the whole atmosphere is raised in temperature. Same thing could be happening. That pulse could be 10 watts on that part of the atmosphere, could be 20 watts down here at the base, could be 5 watts here, whatever. However it is, the energy that gets sent, the energy that ends up in there, ends up getting distributed throughout the atmosphere. It's one question though that I have in regards to this. Why does our what was it, dt dz come out to be 9.75 rather, 9.75 Kelvin per kilometer, which should yield 97.5 degrees Celsius difference from 0 to 10 kilometers. But what we have with our greenhouse gases, it's dt dz is more like 3.3 Kelvin per kilometer, because the difference from 0 to 10 kilometers is only 33 Kelvin. I don't know for sure, but one thing I might suggest is that the density, this was based on a density of the atmosphere being the same throughout that 10 kilometer distance, that the density of the atmosphere was 1.29 kilograms per meter cubed the whole way up. But what is the actual density at the troposphere, or the tropopause? Okay, so this graph shows, I think that shows as the red line, row over row sub naught, and down here is 1 of the density of the air at the Earth's surface. I said it was 1.29, they're saying here it's 1.225 kilograms per meter cubed. But what they've got here is a red line showing that at 10,000 meters, that density is about 30, let's see, what is this? About 35% of the density at the surface. So we might be matching both. We might end up matching both. The actual dTdz might actually end up being averaged out over that entire thing. We'd have to do probably have to do some kind of integral based on that pressure, but it would end up being 3.3 Kelvin per meter on average for 33 Kelvin for the entire 10 kilometer distance. Okay, well that's it for section 8, and I will continue this on another day. For now, thanks for watching, if you have been. Well, I'll continue. I'll see if I can get a chance to look at more of this document later and see if I can have more reaction video for it.